Right. So it looks like we are live now. Oh, sorry about that. Had a man trying past couple of days, but that's cool. Let's see if I can power through this. I am just so happy that bedtime is going to be coming soon, at least for me anyway. So, I guess we'll wait a little bit, wait for some people to show up. No big whoop. Uh, what we're going to be doing today is we're going to kind of look at this code here. Last time I kind of went on and on and on about building these LCGs or LGCs, LCGs, and spent a lot of time doing that. Didn't really talk about ADTs, so we're going to make sure that we're talking about ADTs a lot this time. So we'll start off by first moving this stuff into a file itself. So we can do that quite simply. We'll just make something here. We'll call it rando. Oh, we don't want it there. We want it in our model itself. So we'll make something called rando, and this will hold all of our random functions and everything that we need. So we'll just go ahead and add that. And next thing we need to do, of course, is start getting stuff off of our workbench, because we're going to look at a couple other things. So we want to clear our workbench now. Now's a good time to do it. This code might not be the code that we're with, but it's in a clean enough state that we can move it over. So like we did with deck in the first one, let's go ahead and just move these functions over, see what we need and whatnot. So here we have our little state of seed that we're going to pass in. And then from there, we're just going to, let's see, we need pull random. Seed comes in. Limit index also is something to do with rando, so we can move that out. And again, we're going to be refactoring this, so we'll just move this out as it is, right? So let's grab, well, heck, pretty much all of this. Well, let's move it one by one. Okay. So the first thing we'll do is move out, where is our actual state? Do we even use this? We do for that, but we don't need that in ours. Really, all we need is this modify and get, because all the functions that we have pretty much just use that modify and that get. So this depends on nothing. So let's move rando out first. All right. So we'll move this. This is going to be, oops. This is going to be what we want. So here we have rando, and let's match the same pattern we're doing with deck. So in deck, we have everything and we just modules.exports it. So I don't know if we're going to need rando because we don't seem to interact with that outside of here. So we're only really using pull random, so we do not need to bring that out. Exports. So we don't need to export that yet, or we don't need to export anything yet. It's really these two files or these two functions and the way that it stands right now is what we're going to be using, right? So let's see what we have in rando. Well, we need to bring modify in for sure, so let's do that. We'll do const modify, and we'll just pull that because we don't really need the state. We'll just pull that off of, require crocs and state. No need to really bring that in. So now we have modify in there. We need to bring constant in. So let's bring in our or our combinator here. And it looks like this is the only function that used that, so we can actually take that out now. Okay, and we also need to bring a assign in. So we'll bring assign in because that's also used by this. And it looks like, yep, assign is used but never, or is there but never used. And we can get rid of modify now. Okay, so we got rando moved over and everything we need for rando. Let's see, this is what relies on rando. So let's go ahead and bring that in. All right, we'll make this a little easier to read. Here, we'll just put that down. And we need, let's see, we need get at the very least. And that's the only thing that used get, so we can delete that from there. And we'll just bring get in here. All right, get this all cleaned up and looking pretty. Let's see here. Now we need to bring pluck seed. Oh, and it looks like pull random is actually used outside of here. So let's go ahead and export pluck seed. Or I'm sorry, pull random. So now we can just bring that in and get rid of this. Okay, yeah, it's real boring stuff, but it'll work out. It's something we got to do. It'd be nice to clear all this. Oh, we're not using state anymore. Oops, or are we? Yes, we are. Sorry about that. All right, so now we want to bring in pull random, and we'll bring that in from, where do we want to bring this in from? Require, and that will be model and rando. Okay, so now we have that pulled in. We now need to move pluck seed, and once we move this, that can go here. We need to bring in option, pretty much all of this stuff. So we'll bring this in, and let's clean this up a little bit. B comes, well, we'll keep all the capitals together. LMNOP, so that should go there. And we pretty much have everything there. All right, so now we have everything we need with pull random. We have everything we need with that, and we save it. So since this, we don't really need this. This is kind of our own little helper function to limit something. So I don't know. We probably won't bring this over because that's more of, you know, a thing that we need. So let's execute this. And this should get us back our, cool. So there's our state with execute. So now we have everything moved over there, right? We can lift our seed, do everything like that, and we got all of our stuff behind this in this rando file, with our only output being that pull random. So pretty cool. Now we have kind of a clean slate here. So one of the things I want to address, or one of the things I want to look at here, is we have this rando function, and this rando function is very imperative. Like, we have all these calculations, and then we put it in some state, seed and value, and then we work on that state there. So I think we might be able, if we think of the state monad as more of a way to work with shared state between things, then I guess we could see this as a, how you say, well, one alternative for fixing this up is to kind of move these into an arrow, right? And the reason why I say that is arrows are really good when you have a split, how would you say, like kind of a split calculation or computation. And we have that here because this computation actually depends on seed, but we need the seed back as well, right? But we could use that seed to calculate this value, and at the end of the day we want a seed and a value. So we can do something like that with arrow. But before we do that, let's kind of let's take a step back, sort of. Let's kind of talk about what arrows are. So let's clear our board completely here. We don't need any of this stuff. And we'll talk about arrow. Let's do it this way though. Okay, so we'll make something here and we'll call it pizza. The reason why we're calling it pizza will make sense in a little bit here. So in our model here, we'll create this file called pizza. All right, and then with pizza, we'll just open this up there. This is our pizza file. And inside of here, we'll make something called make pizza, I guess. We'll say, yeah, make pizza. So we'll do const make pizza. Actually, we want to pull this off. Make pizza. And that's equal to that. Actually, for now, let's just require this in, and we'll use this kind of as a runner. So we'll just require in the thing that we need. We'll move log over here so we have log available to us. And that actually needs to come in like this, except we want to type it properly, I guess. And then here we can get rid of the log for now, and we'll require in model pizza. Okay, and we'll just use this as a runner for now. Oops, there we go. Now I can find the module. So here we are in our model pizza. So the reason why I'm kind of going with the pizza is, well, let's just talk about what arrow is. Okay, so I'm sure you've seen, signatures like A to B, right? See how we have this little arrow in here? This is basically talking about a function that moves from an A to another B. So this can be a Boolean that maps either true or false to, say, a string, right? So we have a Boolean, and then that's a function that takes a Boolean and then gives us back a string. So, and that, I mean, that's basically your functions, right? So we could have just something real simple like const f is equal to, we'll take a bool here, and if that bool is true, then we put out true, and if not, we put out false, right? So this is just a simple mapping that does that, right? Just a function. I'm going from a Boolean as an input. I'm going to check to see if that's truthy. I'm going to give you a string back. This mapping can be to anything, like anything really, right? So what an arrow is, remember how we were looking at state, and the state signature is kind of set up like this. You have some A and then a state. It's basically parameterized by two types, the state and the actual bit that's functorial, right? So what an arrow is if we take this A to a B and kind of change the notation of it. So we can take this arrow here and we just place it here like that. So when we say arrow, it's just a, not infix, I think it's Polish notation, or not Polish. I forgot the name of the notation, but if anyone knows, throw it in the chat. But basically we flip it, and the first parameter to it is the input to whatever the wrapped function is, and the second parameter is the actual output of what that is, right? Like what is returned by that function. So arrow itself actually wraps a function from A to B, right? So we can replace that with arrow. So let's go ahead and bring arrow in and kind of see, how we could use these sorts of things. So an arrow is what you call the canonical example of a profunctor. So what a profunctor is it's a type that's contravariant in its left argument, but covariant in its right argument. For us, that mostly means functions, but kind of in the, how would you say, basically for us it's wrapping functions. When we take it from a categorical point of view, there's more things you can do with it, but for us in set, there's pretty much, we can wrap functions with it, right? So let's go ahead and bring in arrow, and we can kind of see what, how to use this sort of thing, right? So the way I kind of like to think of profunctors, and arrow especially, is kind of like a pizza oven, right? So you have some sort of oven that, if you're ever sitting in a Papa John's or something, watching something, you have three very distinct processes to the, or processes, whatever the word is, that center around that pizza oven. So you have an assembly line where you have people that grab and put ingredients on something, pass it down the line, each one chaining its own ingredient on, adding something to it until it gets to the pizza oven itself. Now, different stores might have different pizza ovens that require different things or different trays to put them on, stuff like that, to get the oven to work for it, right? So then it goes through the process of cooking everything. And then inside of that, it cooks. And then at the end, when the pizza comes out, there's a whole packaging process where you actually pull the pizza out of the oven, you put it in a box, and then you ship it on its way for a to-go customer or whatever, right? So how you can kind of think of this as the arrow itself as the center or the oven. And you have different ways of adapting it as the stuff flows into it on the left, and other ways of adapting it on the right. Kind of like with function composition, right? So let me kind of give you an example of what I'm talking about. So we might have this oven here, and we'll say const oven is equal to, and let's go ahead and we'll call this for now an arrow that goes from A to an object, right? So we're going to take any type A, or we would like to take anything that you put in it, and in this case it'll be a cooked pizza, but we're going to use an object, so it's basically attributes on this thing that we're passing through. It just makes it easier to follow. But think of this return object as a cooked pizza. That's all good to go, right? So what we can do with this oven is we will create an arrow, and this will be the center or the center of the whole process, the cooking of it and whatnot, right? So what we need to do is actually lift a function into here. So let's just say that whatever we get back, all we're going to do is take the raw ingredients, the raw part of it, and then we'll take whatever that raw thing is, pull it off of the raw attribute, and put it into a cooked attribute, right? So we can actually do that by creating another function that we'll call cook pizza, because maybe there's different processes or things like that that we want to lift in this arrow. So we'll make our cook pizza, which again just takes an A to an object. Notice we're not inside of this arrow, but the signature here on the left, this is the arrow, that's the right, matches what this type is. So this is going to be our cooker, basically. So to do this, we're going to do a little point-free kind of stuff here. So we will do a const, and we'll call it cook pizza. And cook pizza is going to be, oh, what are you doing? Cooked pizza is going to be a composition, so we need to bring compose in. Let's do that real quick. We'll do compose is equal to require, and we'll do crocs helpers compose. And this is just our normal function composition. Again, if you have any questions or anything like that, go ahead and throw them in the chat. Again, if none of this is making sense or anything, or you want me to explain something, just throw something up in the chat. I'll be able to stop and kind of help with that. So remember the process I was saying. We want to somehow lift in, or we want to take a raw pizza, or a raw something, right? So to do that, let's just use a function. We'll expect maybe, I know it says an A at this point to a anything else, but at this point let's pretend that we only work on objects that have a raw attribute, right? So what we can do is we'll use this prop function here. And prop will basically take an object. If the prop exists on it, it will give you back a just or a maybe that has the value of that prop wrapped in there. If it is not an object or it doesn't exist, it's going to, and that property doesn't exist, it's going to give you back a nothing basically. So we can use that to map over, do whatever, right? So let's use this prop, and like I said, we're going to bring in, or we're going to look for a value of raw. Okay, so to do that, we need to bring prop in, and this is require crocs, and because this is a maybe, it constructs a maybe, we pull it off the maybe namespace because that's where it lives, and that prop. we'll come back. Oh, sweet. Awesome. I appreciate that, Mr. Beckett. Kendrick Beckett says, I really liked your Ramda Lessons video, subbed because of it. So, well, good. I hope I can still do okay things here. Oh, goodness gracious. Arrows needs to take a function. So right now, let's just throw in cook pizza here. And cook pizza will take our function, cannot find helpers. It's helpers. Okay. So now we have this. So let's do oven. And we see that we get back an arrow that has a function inside of it. And at this point, we could run it with anything, right? So we'll do run with. It has a run with function. The arrow does. And let's just put in a blank object. If you see, we get nothing back. So we know that the prop is working properly. If we put in raw and just put yep or true, we see that we get back a just true, right? So the prop goes in, and if we have something, if we make this raw and make it gaw, notice we get a nothing back because it doesn't have that. If we send in an array, we'll get a nothing back because it doesn't have anything on that. So effectively, we can pass anything to this oven, and because of this prop, it's only going to be valid if we get something back. But you'll notice we are saying that we're going to get an object back, right? So let's just bring in, because this is a maybe, we can use this little function here called option. And what option does is it takes in a maybe, it's a point-free function, and it takes in whatever you want the value to be, if it's a nothing first or the default value. And if it's a nothing, it will return that value. If it's something, it'll just return that something, right? So we need this to be an object. So we can just do our point free, and then we'll bring in option here. And now we can option this maybe just by composing in option. And we will put in an object, right? So now we get our object back, okay? So you'll notice here on the good path, so on the bad path, like if something is bad, something is invalid, we're getting our object back. So cool, we match our signature. We are almost there. But we see if we go and change this and actually make this, let's say raw, and we'll just say true. Notice we're not giving an object back. We are actually giving back a Boolean, so it does not match this signature. So what we need to do in the case that we're good is let's go ahead and remember I was saying to go from raw. What we're going to do is return something that's cooked. We'll go object of, and this will let us create an object that will take whatever the value is, and it'll give us an object with the key. That's the first parameter we pass to it. It'll take whatever it gets and make an object with that value and that key. So it just gives you back one object basically. So let's do this, and we'll do object of. And here we'll just do helpers, and this is object of. Boom. So now we can do an object of, and we do cooked. Oh. But we're in a maybe. So because we're in a maybe, right now we're taking this maybe and wrapping it in cooked. We need to actually map over it. So to do that, we will go into here and also do point free, and then we'll do map. So now what we can do is map this function in, and then that's going to take our df to there. That's going to actually take the maybe that we get back from this prop, and it's going to map this function over it. So now we can lift it inside of that maybe space and then run this function over it. So now you see that we get back cooked true, right? So this is JavaScript, right? So typically we wouldn't want to return just a blank object like this. We'd want to return back some sort of record, right? So something that would always have an attribute of cooked. So with this, we can't really get there from there. But don't worry. And what I mean by that is if we look here and say we just pass in true, right? We're getting that back. It would be better if we could give back the object that in the proper form, right? We'll get to that in a minute. Right now, we could do it with some finagling, like we could bring in and say whatever the value was here. Oops. So we could say whatever this value was here, we can option it to that X and then reset it up to do this object of, and like it could get real nasty, but there's better ways that we could deal with that, and we'll look at a few of those, right? But the most important thing here is now we have our oven. We have the center of our machine. So on the left and the right, we need a way to build the pizza up and send it into this oven, and then another way to package it up. And that's where like profunctors, that's where like arrow and stuff come into play very nicely. So let's deal with the contravariant part, the part on the left end. So let's build an assembly line here, and what we'll do is we'll just do const.do, and this will basically just be an arrow, right? And what we want to do on this assembly line, if we think about it, let's just say that an array is a tray. Array is a tray. It rhymes, it's great. So we'll say an array is a tray. An empty tray is a tray with nothing on it. So what we want to do is as we go across our assembly line, we want to add the specific ingredient that we want to build the pizza to send into our oven. And we kind of want this process separate from the oven, right? Like if we have a different oven, we may want to change that oven out and put a new oven there. This will allow us to kind of do that. So we need to kind of think about this in its own flow. So in its own flow, as far as the assembly person knows, is they're going to get a tray that has something on it. And then they have to take something, maybe it's a robot arm, maybe it's something really cool. They need to take their ingredient, do their magic on it, and then add it to the tray, and then pass it down the line, right? They basically need to chain all of this down. We could keep this in JavaScript because it doesn't matter where you lift these. Like we could lift the function into an arrow and then compose the arrows. And we could also compose all of this inside of JavaScript and then lift it as a Contra Map into the function itself. I mean, there's a lot of ways that we could do this, and they all commute. So whether we lift into the arrow first and then map through the arrow, or if we do it all in JavaScript and then execute, both of those lines commute, you know, and even the composition of those commute. So it doesn't really matter like how we do it. What I'm going to do here is I'm just going to keep them in arrows and compose them along the way. So we can kind of think of the assembly line as a whole other machine. Maybe we can move our assembly line out, right? Maybe we want to keep the oven but move the assembly line and switch it out. So I mean there's different ways you can approach it, and because they all commute and it's a functor itself, it doesn't matter. Well, it forms a category, but anyway, never mind. So it doesn't matter where we put this stuff together. We can always put it together outside of JavaScript and then hook it up whenever we need to hook them up, or we could stay an arrow the whole time and hook it up, is what I'm trying to say, right? So let's just say that doe is a female deer. We'll say that doe returns an arrow, and it's going to give us back, it's basically what's called an endomorphism. So we're going to take a string or an array of string, right? And we could think of these as an array of ingredients. But because we're actually, because it's an endomorphism like that, we don't need to write this second string. A lot of times people abbreviate that. So since we know that arrow is always going to be 2 parameters, if we only see one, then we can safely say that it's an endofunctor, or I'm sorry, a endomorphism inside of it. Of course it's an endofunctor, but all right. Anyway, so we have this doe that's going to give us this back, right? And all we're going to do here is we can use this concat helper. And what concat does is it takes any semigroup, and we'll concat two semigroups of the same type. Well, because array is a semigroup, we can just bring in concat and say, give me the dough, right? So this will be our dough. Now let's just go ahead and bring concat in. Concat. And this will be a point free because it's a point free for the semigroup. Oops. And we'll do concat here. Okay. Oops, cannot read property raw of, what am I doing wrong here? Oh, because I have undefined there. Ooh, that's interesting. So we'll run with, we'll just run with an empty array for now. Okay, so that gets us that back. It basically gets us back an empty string, or an empty object. So we have our dough, and what's another thing that goes on pizza? So we can have sauce, right? So we'll do sauce, and that's the same signature. Doesn't really matter. Okay, and this will be sauce. And again, we'll just do the same thing. It's all mechanical. There's ways we can clean this up, right, by using mconcats, some other things. But this kind of, I just want to show the mechanical nature of this. There's much better ways to represent something like this, but it makes a lot of sense, right? So we'll just go with the normal cheese pizza. How about a cheese pizza? And this will just be cheese, right? So we have meat, cheese, and sauce. Or not meat, no meat. Oops. All right, we'll clean this up a bit. And now we have this. We have a way to actually put our sauce and our dough and all of this great stuff together. So because these are, how would you say, because these are, well, actually, let's just see what this looks like to make a cheese pizza, right? So what we can do to make a cheese pizza, or to actually assemble the thing, is go in and we will say that a cheese pizza is taking dough, right? And dough is just an arrow. And then from there, we're going to compose. We'll take our dough, and then we'll compose in our sauce. Okay, and then we can also compose in, after that, our cheese. Cheese, please. And now we have a cheese pizza. So let's see what that looks like to have a cheese pizza, right? I bet it's very exciting. So if we were to take our cheese pizza and we do run with, and we give our empty tray, we see that we get back our pizza that's dough, sauce, and cheese. So all we did was just composed all of these functions together. Now we could have composed them just fine, just using a normal compose like we have, like we did here. Where did we use compose? We could have done it that way, but it gets us this machine that we can now do things with. We can adapt it just like we did with the oven on the left and the right. We can do whatever we need to do to adapt it. So because this is what's called a semigroupoid, so anything that has a compose on it like this, any ADT, is what's called a semigroupoid. So we actually have in Crocs, we have a compose S that'll allow you to compose together semigroupoids. So instead of setting this up to, be this way and doing more of the fluent style of .compose, 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 we can let this compose S handle all that for us, right? So all we need to do is, since we're composing in, we just do it the opposite way. And we want to take our cheese last, our sauce next, and our dough finally after that. Okay, so now we have that compose S, and this should get us the same exact thing. And because we are composing, this is different than functional composition, because you pass it functions, it gives you a function back. Here we're passing it semigroupoid, so we'll get a semigroupoid of the same type back. So as we come in here, We just need to bring compose s in. So we just go to the end of that, and we bring in compose s and do the same thing here. Okay. So now we have our compose s. And if we go down to the bottom, we'll notice that we run it and we get the same thing, right? So you can just use, if you want to use more of a point-free style, you can chain these arrows together by using compose s, or if you want the more fluent style, you can just call dot compose on each one and kind of pipe them together like that. So you have options here. There's also a pipe s2 if you want to reverse the order of this. You can have pipe s. So now that we have, and we've looked at compose, now that we have this, let's go ahead and just try to run our cheese pizza through this. So we'll start with our cheese pizza here, and then here we'll compose into our cheese pizza, because remember, we have, it's an arrow, it's its own machine, but this would be a machine that was configured to put together a cheese pizza. We'll then compose in oven, right? So now when we get it back, we didn't get this back the way that we were expecting it, right? Because even though it takes an A and gives us an object back, we need to actually have this value of raw on it. We need to have raw available to it. And if we don't have raw available to it, it's not going to cook the pizza the way that we want. So what we need to do is adapt our oven so it would be able to, how would you say, work with the pizza that we're getting from here. So ideally, we'd like to take the tray that we have and then wrap it inside of something that will associate that tray of ingredients to a tag called raw, which we know how to work with. So this is where Contra Map comes in. So what we can do is we can set up a Contra Map. And what Contra Map does is, because we're expecting something that takes something with a raw, like it takes an object that has a raw property on it like that, and we're not getting that obviously, we need to take whatever we're given and then adapt it to that. So what we need to do is turn this from raw, the way that it is now, into something that takes an A. And will accept pretty much anything and will give us back the desired result. So what Contra Map does is it will take, if we look at the signature of it, right? So a Contra Map is for any F that has a, we'll just do an AB, I guess. We could do it with a fixed type, like if we had Boolean here, but we'll just do it like that. If we have that, we need a function that will take something from a C to an A. So basically, we want to take our other A and move it into what the, or we want to take what we have. Let's do it like this. So what Contra Map does is takes a function that goes from in, if we have a C to a B, it will take an A and move that A to a C. And then that's going to get us back another F. Well, then it'll take the, let's do it like this. So we take an A to a C, and then we have something now that will take something from a C, and it'll give us back an F or whatever that goes from a to a B, or an AB. So when we map, we're usually changing this thing on the right and we're moving to the right, right? So we are going from one type to another type to another type. We're going down the line. What this is doing is it's adjusting the front of this. So we give it a function that can be from an A to a C, and all we do is compose that function on here, and it'll give us back an adapted profunctor, or an adapted contrafunctor, that will now take an A and give us back well, it'll now take an A, and then when you run it, it'll give us back a B. So that's exactly what we need to do here, because we need to take whatever it's giving us, we need to wrap it inside of something that will take that raw, right? So how we do that is we can just use object of, we've already used it, and we'll just wrap that in raw, right? So now anything that we have, object of, it's going to now give us back a function that will lift this, or an arrow that's going to lift this and be able to run it on the inner machinery where it pulls the raw off and give us the result back. So that's what these Contra Maps do. They let you adapt these machines or these ovens or whatever to take or to modify the input before it comes in. So now if we run it, we see that we get back what we're looking for. We now get a cooked dough sauce cheese, right? So maybe we don't want to, so now we need to deal with the packaging. We dealt with the left side. We put the assembly line together. We then assembled this cheese pizza using our cheese pizza machine, and then we composed that with our oven. But our oven needed to be adapted because our first machine didn't adapt properly or did not give what the pizza oven needed. So we changed it around, so now the pizza needs it. Or the pizza will now be in the proper state that we need, right? Now we still have the problem here if we like put in true or whatever, we don't get back something that we would expect. You know, we'll fix that here in a minute. But before we fix that, run with, what's going on there? Hold on. Unexpected token. We have our compose. Why is there an unexpected token there? Oh, because of this. All right. Okay, so now we'll just do that and then put that. Hey, Julio, how are you doing, sir? All right. So, well, now we're running into the problem where with our assembly line, right? But if we were to take the, that's awesome. But if we were to take the oven out of it, just actually put this with the oven and call run with on that, we'd see we still wouldn't get back our true. We still wouldn't get back like a cooked true like we would expect. Okay. Oh, we do. We do, because we were able to lift it. Never mind. We were able to cook that. Sorry. That's right. All right. Totally went off topic here. So now let's take a quick little view on how we could, how would you say, package this up, right? So we don't really need to lift it into another machine. Let's go ahead and put this back into our other flow, our normal flow. There we go. Okay, so now we have our cooked pizza as it runs through our machine. So now what we need to do is package this. So we don't really need to, the package doesn't need to be a machine. It's just something real simple that will go ahead and wrap this pizza, we'll just say in an array, right? So here we can just make a function, and maybe the packaging comes with it, right? Hold on. So let's just make a function here. Just a normal JavaScript function, which will take, we'll call it package, okay? And then package takes whatever it is, and then it lifts it into a box. We'll just throw it into this box here. We could have used like an identity or something like that, but who cares? We're just going to wrap whatever it is inside of an array, okay? So what package does is it takes any A, and it gives us back an array of A. Okay? So what we can do now is say the packaging just comes with it. Maybe it's just built into the specific oven that we have, right? So what we can do is just map this on. And like I was saying earlier, it doesn't matter whether we lift and have everything in the arrow or, oh yeah, see? Scott J. Anderson's right. We could make this super duper cool and complicated to actually make it crust and make it. He was saying cooked dough equals crust. So we could even dip down in each one of these and figure out, make a mapping of how each ingredient cooks. And that could be part of the whole cooking process. It doesn't matter how complex that inner machine is, because we can compose all kinds of things together and still work on it as if it's one little machine in the cog. So that's very, very good observation, J. Scott Anderson. So now what we can do to package this up is we'll just go ahead and map package in. And you see we get back everything wrapped in the actual array. So it's kind of weird the way that my screen's showing it. But that's an array that has an object in it that has cooked with the bits in it, right? So because this is a profunctor, instead of anytime you see yourself doing this contra map and a map right after it, or a map and a contra map, it doesn't matter how it's reversed. There's actually a function for this called promap, right? So we can just do a promap and then take our contravariant first, because remember, that's the left parameter. So we can just take that, and we can now use package on the right, and package, and just delete that, and we get the same results, right? So promap is the same thing as doing a contra after a map or a map after a contra. If you see that pattern, you can promap those. And again, because it's a functor, these right now, these are just simple functions. These can be whole new compositions. So in JavaScript, we might have a whole flow. We can put together a flow, and it's just a function, right? It'll map the same. All the arrows still commute because it's a functor, even with having these functions inside of these other functors and all that. It doesn't matter when or how you do it. They'll just commute and equal the same thing. So okay, now we got the oven. Now we got that. Now one of the things that's kind of weird here, right? And just I want to give another kind of aspect of what this is, or another aspect of this arrow. Let's make this cheese pizza. And that is pretty much the same thing. It's just an arrow that gives us the strings back and all that. So because this is a, I kind of want to show there's an aspect of this that makes it a strong profunctor. And that's whenever you have some sort of product type that's inside of the functions that you're doing. And by default, we pretty much rely on pair for this, right? Let me take a little sip here. All right. So what we're going to do is we can clear this part out here. We can do a little bit of cleanup work here and get this cooked pizza to actually be a little, how would you say, give us the results of whatever it was that we intended it to be to begin with, right? And even though we always option to this, if we ever got into, hold on, let's just do our oven here so I can show you what I'm talking about. Okay, so that will get us our cooked. Now let's take our adapted part out of here. Okay, and I'll show you what a strong profunctor can do. Okay, so now that we have the adapted part done, all of that stuff, let's go ahead and run with, if we have raw in, and we'll just do true, you'll see we get back our cooked true, things like that. And if we don't put it in, we get back, oops, like say we pass null in. Oops. Okay, so we'll pass in 45 or whatever. See, we didn't get that back. And actually, let's just put in a string called teeth. Okay, So we're going to run this with teeth. And maybe we want our oven to be able to cook teeth properly. But the way that it's set up without this adapter or whatever, there's no way that we can really cook it the way that we want, right? And that's because of this and what we're setting this option to. What we want to be able to do is maybe make this a, hold on. So what we want to do is maybe have this oven give us back something called, give us back a maybe, right? Not have the option of like whatever, I'm sorry, not give us back a maybe, but we want to be able to have that original value out there without having to do something like this, right? So we could just do this def and then pass this in and then pass def, but now we're not really point free here, right? So I mean, this will get us what we want, but it didn't wrap it in the bit that we needed. So we'll have to actually reconstruct this object outside of this and deal with it that way, or we can use the strong profunctor part of this. And what the strong, or what the using a pair allows you to do is to split your calculation, right? Or your computation. So what we want to do is take whatever comes in and split it. And then we want to work on one side of it. And if something is bad on one side of the pair, we want to be able to replace it with whatever the default value was. Or maybe we want access to whatever that default value is. Who knows? Who knows? All kinds of things that we might want to be able to do with that. But it would be nice to have our original value untouched and unscathed, so that way we can revert back to it. And we don't end up with a situation like this where we have to just build out this logic and repeat it. If you ever have to do things like this, like bring in a def and then set this up, call that so you can use it in here, chances are you could probably do some more refactoring around it, right? So with Arrow, we have that opportunity. Another way to do this if you're using Ramda is to use Converge. Converge will allow you to split the thing up into multiple values in an array, and then different functions can run on each of them, and then you can converge them back based on how each one is calculated. Same sort of thing, but this is done with ADTs instead of functionally, right? Instead of using functions. So we need to do a little bit of changing here to kind of get this to work the way that we would like it to work. So first thing we'll do is actually change our oven. We still want to be able to cook the pizza, but what we need to do is get this to work on a pair. Okay? So what we can do is split this pair out here. And we can do this by doing a Contra Map. So didn't we have a Contra Map? We have a Pro Map there. All right, so we can do a Contra Map. And we have a function called branch inside of Crocs that is for doing this. It'll basically take whatever value you have and run identity on it for both the left and the right. So you have the same value, one on the left, one on the right. So let's go ahead and bring branch in. Okay, now what branch, like I said, branch will split this into a pair, because remember, for this to be, for us to keep that state around, we need to split it into a pair. And we will do Crocs pair, and this will be branch. Because it gives a branch back, or because it gives a pair back, it's going to be in the pair namespace. So then all we need to do is just call branch on here, and we can see what we get. Okay, so now what this gives us back is a function that has teeth and teeth in it, right? So it cooked the pizza, did everything it needed to do, at least this oven. We put teeth inside of it so it could cook the teeth for us or whatever. Well, it hasn't cooked anything yet, but one of the things to notice is on the left side it says teeth, and on the right side it says teeth. Anything we put in here We could eat feet maybe. Oh my gosh, these are horrible things to eat. But let's put teeth back. Okay. So this basically, when we did this, it now set up this thing to work on pairs, right? But say we want to run our function, the cook pizza. Say we want to run that over our, and actually, to make it even easier here, if we do this, you'll notice we get a nothing back. So we basically just took the option out of there. And you'll see that we got a nothing back because it's not valid, it's not going to work with it, it doesn't have that prop raw, all kinds of reasons why that's not working, right? Okay, so now that we have that split out, we get our nothing back, and it basically turns into a nothing. We then at some point, we then need to merge this back together. So right now, and let me put this back so you can see what we have, see what the rock's cooking. It's a lot easier to just see what's going on as we do these sorts of things. So what we want to do is then merge this in, right? I'm sorry. We then want to map, and we'll do a merge function. And what merge does is it works on a pair, and it'll give you a binary function that the first one is going to be the first parameter to it, or the first argument, and then whatever's on the second side of the pair is going to be the second. So it allows you to take both parts of the pair and have a binary function that merges them together. So that way you can control how the two parts can be merged together. And that's pretty much what we want to do, right? We want to merge these together and be able to, how would you say, make them one, right? So let's bring in merge here and have ourselves a little merge party. And this is going to be, of course, on pair because it only works on pairs. And we'll do that merge. So let's go back downstairs. And what we want to merge in is basically we want to take whatever's on the left. This is going to error. Oh no, it gives us back the function because merge doesn't have anything there, right? So this basically gives us back the maybe. Now, what we want to do is option this maybe. So on one of these sides, whatever we decide to calculate is going to calculate this cooked pizza, right? And what we want to do is take that option that had the original value, and we want that to option the maybe that we're going to get back from the other side. Okay, so right now we're getting back a nothing. We're going to do whatever because teeth isn't a thing. We'll then merge with option. And this is going to error because pair is required for the second argument, right? And we don't really have a pair right now. We have that maybe. So we're set up to work on the pair as a whole. So what we need to do is actually apply this function and tell it where to work. So how we do that is we then go in here and do second. And this is saying, whatever you get back, I want this function to run on the second part of the pair. So now if we look, it gives us back teeth, right? Because that's what got merged in, was those teeth. So what we can do now is, oops. So what's going on? If we don't see this, let's see what this map gets us. So we see over on the right, we get nothing back. So it's going to give us back the teeth. Okay? Just like that. But if we then merge, it's going to get us back the actual teeth that we requested or whatever. So what we really want to do after this is adapt it. But let's see what happens when we get an actual valid result. I hate when I delete one of those because that happens. Okay. Oh. Okay. So now what we're going to do is we'll run it with raw. So when we get it back, we actually get back cooked teeth and all that. Otherwise, we get back something that this will allow us to, when we put it this way, and if we look here before we do the merge and see the pair that we get back, we see that we get back on the left side. So we can do that, and let's look at dot first. Oh. So down here we'll look at dot first. So on the left side, we see on the first we have a raw teeth, which is what we passed in. And if we look at the second side, we have our just object, which is the valid thing. So it actually returned the valid object since it went through. But if we just have teeth here, and we look at that, we see that the second is actually a nothing, and then the left is the original value. So by doing this, it lets us work on something in one aspect or in one chain or one branch of execution, and also work on it in another aspect. If we wanted it to work on the first or do things like that, we could set this to first, or we could set it to work on both. It doesn't really matter. Yeah. So now that we have this, that's very quick explanation. Well, not very quick, but kind of hand waving at the strong portion of this and all that. I started realizing how out of time I was running. So I kind of rushed through that. But let's look at our refactor that we could do for our actual rando using the stuff that we just learned about arrow, right? So we have this pizza, we have that. So let's go ahead and let's get rid of log here. We'll bring log back here. We don't really need to have anything outside of here. Okay. And we don't really need to bring the pizza in anymore. So now we just have our log, cannot find, all right. So this needs to actually go back to there. Now we have log. Okay. So now let's see how we would maybe use rando or use arrow to kind of refactor rando, right? And we'll just go through this really quick. It's being recorded and things like that, so you can always go back and just look at it and see what's going on. But we have two different calculations like we did here that are dependent on that original seed value, right? So instead of doing this imperative stuff in here and putting these calculations like that, what we could do, and let's actually copy that. So we will do this. Actually, no, we don't need to do that. We'll just go here and we'll copy that and we'll call it rando arrow. Okay, so this will be our rando arrow. It's the same thing. This way it keeps our current stuff intact for the next version. Now we can get rid of, or here we'll just do const, and we'll grab, what did we expose from rando? Pull random. So we will expose pull random. Okay. And we'll pull that from require model, and we will do rando arrow. Okay, so if we set this up the same way that we had it before, we'll just see that, yeah, it's still logging out properly. What happens when we call pull random? Who knows? Let's see what pull random is. It's a function, so we'll call it like that, and we get back a state function, and we will do run with and we will pass in a seed of 23. Nope. Okay, so now we get everything back. All right, so that's basically what we're looking for, is anytime that we pass in 23, we want to get back that. So we can, instead of doing run with, we will just do execute with, so we can see what the state is. That's all we really care about in this for now. What is this saying? Nothing. Okay. All right. So now that we have this, let's kind of do our refactor here. Okay. So we're going to bring in arrow. So we'll do const arrow, and that's equal to require crocs arrow. So much fun, except we should spell it properly, of course. Any questions? Nope. All right. So now that we have our arrow, we're also probably going to be using that branch and merge and things like that. Let's go ahead and, using this rando function here, let's pull these two things out. Let's pull out each of the different computations that we have going on. So we'll create something called calcseed, and we'll say that calcseed gives back an arrow and integer. Okay, it's actually an arrow integer, but it doesn't matter. Since they're both the same, it's an endomorphism, so you can just say integer, and because we know arrow has two parameters, it must be that. It must be a endomorphism. Okay, so what calcseed does is, all we really have to do is take arrow here, and we'll just take an x, and we just take this, right? It's basically just this calculation here. Let's go to the end, and we just plug this in as so. Okay, so now we have that calcseed, and that's kind of its own machine, right? We have our own machine, just like the pizza analogy or whatever. And then let's take the value. So what we need to do is actually take this value, and because we're dependent on the seed, we're going to have to use that strong profunctor, because this is a computation that needs seed, right? So here we'll just do our little arrow, and then we'll do another x, and we'll basically take this. Okay, but there is no seed here, as we'll see, and x isn't used, so we basically just need to go into here and replace this with x. So now we have two separate things that are actually being used, two separate functions that are, or two separate stages of computation, right? So now we'll just make a function here called genRandom. All right, so now we're adding another function here to put this together. So already we're kind of seeing, you know what, maybe this isn't the best solution, but it's a solution for now, and we'll just keep going with it. But in order to get this to work, we need to actually we need to have some way of putting these functions together and interpreting this new arrow type that we're introducing to our already available state, right? So genRandom is just going to be an arrow that takes an integer and an object, right? So an object integer. The state is over on the left side here. Nope. An integer object. Okay, and then value, of course, is an arrow that goes from arrow that takes a pair of ints. So we'll just do pair integer and a pair of, and then that returns us a pair of, oh, it doesn't do that yet. So sorry. So this will basically take a an integer and give us back a float. Okay. So that's what this is doing. It takes an integer, it does all of this mathematics on it, makes things so awesome. And even if it's not an integer, it's going to make it an integer here whenever we do that bitwise calculation. And then that's going to get us back a float. Okay, but we still need to get this seed thing here, and we'll do that with this. Okay? So with gen random, we need to actually do this seed calculation before we do the split. So what we're going to do is we'll do const gen random, and gen random is then going to get us back we'll do calc seed, and from there we'll just map in just like we're doing our map. So once we calculate our seed, we then need to bring in our branching, right? So we need to take the result of this function and we need to branch it so it's in a pair. And then we have this pair available in two places. Because we're going to need this seed for the calculation for the value, but we also need to return the seed, so we can't step on that value. We need to hold on to it for a little bit. So what we're going to do is bring in branch, and just like we did in the other place, we'll just require, and we'll do crocs pair and branch. Okay, so now we have our boolean branch in. So here we'll just call branch, and this is basically going to take whatever this calculated seed is, this value, and it's going to set it up to branch the calculation, right? Okay, so now next thing we need to do is we need to take this value that has the pair inside of it, and we need to compose in the calculation of our value, right? So here we're just going to do compose, and then we'll bring value in. And this is going to compose that in. But the issue here is we are taking an integer to float. Remember that we need to work on a pair, or we need to take a pair in, because that's what this is going to give us. This calculate seed's actually going to give us the, once we give it back, it's going to give us back a pair. We don't want, or we're not set up to work with a pair here. It's real simple to do that. All we need to do is go second, and now we're set up to actually be a pair. And this will be a pair of integer, and then a pair of integer float. Okay. I feel like I'm spelling that wrong. Nah, I think integer is spelled wrong, but I don't want to deal with it right now. Oops. All right, so here we'll just go ahead and throw that in there. So now we're set up, and notice that this turned an integer into a float. By calling it second, you'll see that on the second part of the pair, here it should be integer, integer. We're going to not touch this first integer, and we're going to map over this part and go from an integer to float. Okay? So now if we save it, of course, it's going to be a problem because we don't have the seed. We need to actually do something here with this value, right? And then actually, so now that we have this, we know that it's returning an actual pair. We know that there's a pair coming in, things like that. So we can map with a merge on this. And remember, merge is basically takes a binary function that'll allow you to merge stuff together from a pair, both sides of the pair. So we do our merge, and we bring this in for our merge. Typing is very hard, apparently. All right, so now we will need to set up a binary function for this to do, or to actually merge. And you know what? You know what? We could do it this way. We could do it this way, but I don't really like doing the merger there. We might as well just take our pair and then map in and call pair to array, right? Because that makes more sense. And this will get us back a pair that has an array on it. So now all we need to do here is do const, and since it's an array, we can use destructuring here, and the value is going to be on the right and the other part's going to be on the left. We can then just do seed and then value here. But you'll notice, and then anyway we call gen random, and with gen random all we want to do is run with x. And that will basically just run our function, do everything that we need to do. What's going on here? All right, so then we map, and we map this. I thought for sure. Hold on really quick. Hold up, wait a minute. Let's just do a quick little loggy poo here. GC, hold on. I'm telling you all kinds of lies and fibs and horrible things. So let's just do a quick little x, and we will do console.log x, and here we'll just return x. Okay, so let's see what this returned. Okay, so that does have a pair, and it does throw it in there. So that is good. I thought... okay, so instead of doing that, I thought it had a, it might be a missing a version or something here. So what we'll do here is we will just do p dot first and p dot second. Okay, cool. And then that gets us the bits that we need. So now we see that we're able to and it still works by chaining these in and doing all this stuff. But we were able to use that to move these calculations out, right? But at a cost. Number one, we had to bring in a lot more functions. We had to create this thing to actually put it together in a flow. We had to do a lot of kind of weird things. And in my opinion, this does not read as well as the simple, and just to see what it looked like. See the difference here? We've added many, many more lines of code. And if we look at our rando function, this reads like, I can figure that out. Like in this case, the imperative is a lot better than this arrow implementation that we came up with. So in a lot of times you'll run into this when you're refactoring things and you think something like kind of lays out very nicely. Sometimes it doesn't. Sometimes it's like this. It just doesn't lay out very well. And at that point in time, you need to just ask yourself and be like, wait a minute, am I missing something here? And in this case, I would say that we don't go with the arrow refactor. I think there might be something that we're misunderstanding about the state monad. And I'm wondering if we kind of drill down on the state machine aspect of it, what that's going to mean to us, right? Like what possibilities does that open up? Because even though we've kind of alluded to it in saying that, hey, yeah, it's a state machine and these are transitions and stuff like that, just by implementing it this way, this isn't really implementing to a state machine. It's more implementing to the pattern of I can work on mutable state, right? Which is just one small aspect of the state monad. It's one implementation type. This, on the other hand, so what we'll do next time is we'll kind of dive deeper and look at the state monad not as a way or a means for you to share state between functions, but what it means for it to be an actual state machine. And from there, we should be able to see the refactor that we need to do for this to get this to, number one, get rid of this imperative bits, and to make this act more like a machine, a state machine. So a lot of times when you're, at least for me anyway, when I'm building a lot of these, I'll do, even though I'm not writing imperative code, I write my code in a way that I do this, then I do this, then I do this, then I do that. It's very procedural. And certain steps in the flow depend on other steps to happen first, just like I was writing normal, like procedural code. And that's what happened here, is we're writing this in a very procedural way. This does this, does this, does this. And then these things need to happen before these things happen, right? When we really need to start thinking about it of, this is a type, this is a certain type. How can I combine this type in an abstract and way that is unaffected by when or how I combine it with other types in the chain? And then we start to get the real power of these ADTs. And that was one of the things that was really hard for me to do. Like, async makes sense to me. It's very sequential. I go get this web request, I put it together, I do things like that. But there's other ways to use these types where I build out my data structure, I look at what makes sense for what this data structure is, and then I figure out ways to combine it together. And then later on, in ways that aren't affected by other steps in the procedure, right? And that's what's going on here, though. Like I was saying, we took a real procedural approach to this, when really, if we think about this as a state machine, we'll see that there's a much better way to represent this, and a way that gives us more flexibility and keeps us from doing, imperative things like this. And there's nothing wrong with imperative things like this. You'll notice in Haskell there's do notation, there's lets, there's things like that. Sometimes it makes more sense to be imperative or use a fluent style instead of a point-free style. And you should use the style that communicates the code, right, in my opinion. And stick with that style. So from what we've looked at here, and not just stick with it. Like, just don't use point free just for the sake of using point free. Use point free whenever it makes sense to use something point free. So even though we were doing a lot of things here, and this is a bad example, but even though we were doing a lot of things here, point free inside of here, we still represented most of these as in a fluent style. So we used a little bit of both. We could have made this all point free with like map and things like that, but there's no reason to do any of that unless it makes sense to do that. I think this reads a little bit better. We'll make it read a lot better with our next bit. So join me next time. What we're going to do is we'll look at state machines like this. And we'll see how this real simple state machine that represents a vending machine actually represents things like Redux, and pretty much every app that you've ever created ever, where you've had shared mutable state, was actually some sort of state machine with horrible effects. But with the state monad, we can actually model these same deterministic finite state machines. So next time we'll build out a quick vending machine, and then we'll use the knowledge that we have from the state monad to actually do the final refactor for this rando bit. So that's all I have. Thanks so much for joining me. We're steadily creeping along. As soon as we get through the explanation of the state monad, everything's going to go a lot quicker because there's only a few things we need for our game. And then the next thing we're going to do is take all of this model, and we're going to use HyperApp. We're going to build a HyperApp application that will use our model, and instead of like setting up reducers or actions or things like that, we'll just blindly, or we'll use this model to build out the different states of our game, and just let HyperApp deal with the fact that it's a state monad and things like that. It's pretty interesting stuff. So join me next time if you want, and I will see all you wonderful people later. It's time for me to get some sleep.